Hello, everybody. We are going to start our today's webinar in a minute or two. So we are still waiting for some participants to join us. So please stay online and we'll start in a minute, let's say. Okay, hello everyone. I'm Wojtek Mróz from Eurosite Secretariat, European Land Conservation Network. I've got a great pleasure to welcome you all on our next meeting within remote sensing, Eurosite remote sensing webinars. So before we start with the content of our meeting, I would like to say a few words about our rules. So this webinar will be recorded and shared later on. Please send all your questions to the Q&A button down there. You should find it. So any questions? You can also use chat for pasting some links, whatever. But if you would like to ask a question to our speaker, so please use Q&A button. As a rule, your microphones and cameras have been turned off. Yes, so I hope that more or less we are all together now. So yeah, so now we can start. So it is the second series of our Eurosite remote sensing webinars. The first one was organized last year. We're talking about drones, also some software for bird cams and some other very interesting issues. But this time we would like to focus more on satellite images and this kind of remote sensing tools. And this webinar will be focused on using Earth observations to inform on changes within protected sites. And our guest today is Richard Lucas from Aberystwyth University. But before we start and before I will give the floor to our speaker, I would like to tell you just a few words about our network, Eurosite, European Land Conservation Network. And the main mission of Eurosite is to provide opportunity for practitioners to network and exchange experience on practical site management. So it is exactly what we are doing today. We are trying to share knowledge with our members and non-members about how to use remote sensing for better natural site conservation and management. And within Eurosite, you can find 6 working groups: Economics and Ecosystem Services Working Group, Wetlands and Climate Change Working Group, Eurosite Management Planning Expert Group, Remote Sensing Support Group. So this is this group that is organizing our today's webinar. And Peatland Restoration and Management Group. And the last one just launched, it's Agriculture and Biodiversity Conservation. And our network consists of 72 members, including 41 organizations and 31 individuals from 24 countries across whole Europe. So it includes both governmental and non-governmental organizations, individuals. And we are focusing on Natura 2000 sites, but not only on any other kind of natural areas in Europe. And our secretariat is based in Tilburg in the Netherlands with 5 staff members. And I would like to introduce now the chair of our remote sensing working group, Clive Harford from Wales.
Okay, thanks, Wojtek. Okay, I'm just going to spend a minute or two just saying a little bit about the work of the remote sensing support group before I hand over to Richard for the main event. The remote sensing support group was set up primarily to form a link between the sort of Earth observation sort of technical specialists and nature conservation practitioners. So to facilitate the dialogue between these two groups, because we were aware that they tend to operate in different spheres, but increasingly the Earth observation has a role to play in our sort of observation and monitoring of natural habitats. So the purpose of the group was to facilitate that. Now the way that we would ideally be doing this is through setting up a series of hubs throughout Europe, and we have sort of in theory at least got 12 of these sort of planned for countries throughout Europe where they can hold meetings in their own language, and where these can be face-to-face, so that where typically there would be maybe a subject area covered in the morning, and then the afternoon would be a surgery session where the practitioners can ask specific questions about remote sensing to the Earth observation technicians present. And I'm hoping that we can still do this year, maybe not for a few months yet, and certainly not internationally, but within countries. There's a hope now, I think, maybe with the vaccines and everything else. We cannot make any promises, of course, at this point, but hopefully this is the way it will work out. And we'd be thinking maybe mid to late summer there might be a chance to hold 1 or 2 or 3 of these national events, and at least get some face-to-face stuff done this summer. So that is the hope. In the meantime, where we can sort of at least sow the seeds of some of what is happening and start the dialogue. Okay, that's pretty much all I have to say for now. So I will introduce our speaker, Richard. So Richard Lucas, he holds the Sir Cymru Research Chair in the Earth Observation and Ecosystem Dynamics Research Group at Aberystwyth University. His key achievements, of which there are many, include the generation and release of Australia's mangrove portal and plant biomass library, and the development of the Earth observation data for ecosystem monitoring system, which is for routine monitoring of land cover and change. He's currently leading the Living Whales project, which facilitates the development of national land cover for support of the international conservation and restoration and sustainable use of environments. At this point, I will hand over to Richard, and he can talk us through his presentation.
That's great. Thank you very much, Clive, and welcome everybody to the presentation today. And it's quite interactive, so feel free to ask questions. I'll be presenting over periods of 15 to 20 minutes, and then we'll stop for the questions, allow you to sort of take some of it in as well. So put the questions in the chat, and then yes, feel free to ask anything you like here. Okay, I will share the screen now. So that's that one there. Is that okay, Wojciech and Clive? You can see the screen?
That's perfect,
Yeah,
Richard.
Yeah.
Fantastic. So the title is Using Earth Observations to Inform on Changes Within Protected Sites. And what I'm going to talk about is the role of Earth observations in terms of availability and accessibility. Constructing then land cover and habitat maps from what we call environmental descriptors. Describing and then quantifying change. But then what I really want to emphasize is a positive change, how we can actually do something slightly different. And this was based on work we've been doing with people over in Europe and Australia, and also with Planet Labs, for example. And we gave a presentation recently on that. So I wanted to convey that to you as well. And then proactive engagement and involvement, how to get people involved in that beyond what you're doing already. So in terms of the role of Earth observations, availability and accessibility, what we have is a new era in effect. So we have satellite radar, which is suddenly becoming widely available. It's quite complex to process. This is from the Sentinel-1 radar. It's basically about 6 centimeter wavelength turned C-band. And what it does, it basically, the radar transmits energy to the Earth's surface. It interacts with different elements of it. So the three-dimensional structure, the moisture content, and so on. And provides really a lot on the structure. And here you can see the sort of the water is very clear, and you get different agricultural lands and heathlands and so on for say, Snowdonia in North Wales. There's 2 satellites in orbit, and they're providing 10-meter resolution. And they're there every, it's about every 12 days you get a good image there. Just it's automatically going through. So the advantage of it is it sees through the cloud, and at places like Wales you get cloud-free observations, and they're providing information which you wouldn't normally get from an optical sensor. So the combination of these over time can give you things like water hydro period, how often it's the water's in the landscape, for example, and it can give you information on what the forests are and so on. There are other radar sensors around, and they would include the L-band, which is things like the ALOS 2 Pulsar 2, which is Japanese L-band radar. And that's, we're using that to get information with C-band actually, to get information on the biomass of woody vegetation, because the longer wavelength, 25 centimeter, gives you this, gives you information where the wood is. And there's other sensors coming forward in the future, like the P-band, which is 68 centimeters and so on. So these radar sensors, they offer chances to really interrogate the structural composition of landscapes. They are quite complex to process, but that's becoming much, much easier with some of the toolboxes that the European Space Agency and others are putting forward. And the exciting possibility is the NISAR sensor into the future, which is L-band radar globally at no cost, and that will give you, in combination with C-band, a completely new perspective on what's happening in the landscape. So you'll be able to look at much more forest biomass and so on, changes like that, water under trees. Most of you are familiar with the optical sensors, which is Landsat. The advantage of Landsat is it goes back to 1980s, mid-1980s. Got a full-time series, and in cloudy environments, it wasn't, there were, early on, there wasn't that many images around. But as you progress now with the Landsat 8, and more recently the Sentinel-2, you've got a lot more opportunities to observe the landscape, and obviously the frequency of observation with different sensors like the Sentinel and the Landsat gives you a much better idea of changes and the opportunities for getting cloud-free images. They observe in the near infrared, the visible, and the shortwave infrared, which means that you've got information on the moisture content, the pigmentation of the landscape in the chlorophyll, for example, in the foliage, and also the leaf structure. You can see the orange areas of in this particular case. For the agricultural land, you've got the forests in here, and then the grasslands, the amount of dead material. There's all sorts of algorithms you can use, like looking at fractional cover, about bare fractions, green fractions, and so on. So there's a lot of attributes you can take from that image set, and they can be used, they are used a lot for land cover and particularly change classification. It's 10-meter resolution, again, every 5 days. There's 2 satellites, and the idea is they keep on going. So it's the consistency over time is really critical. The other types of sensors, which are commercial, but they're becoming increasingly sort of available, is the sort of planet data. There's worldview and other ones as well. And planet's a really interesting one because it allows, daily observations, cloud permitting, in the optical spectral wavelengths to observe. This is going forward, apologies, I'll try and keep that so it's not doing that. So it's observing in the visible and the near infrared, but the new super doves are doing in the red edge, and that's really good for tree species discrimination as well. And particularly if it's complemented with airborne LiDAR. So for example, in some countries, I believe Slovenia is one, Wales were doing one at the minute, where national coverage at 1 meter resolution with LiDAR, and that allows you to look at the structure of the forest. So the key thing is there's leaf on and leaf off. this happens to be a leaf off. We're doing a leaf off at the moment in Wales, but then there will be a leaf on. So that would give you actually the height of the trees and of the land surface underneath it as well. But the leaf on isn't currently, we're not doing that at the moment in Wales, but it would be great to have that. But it gives you an idea with the conifer forest, which you see down here. If you've got leaves that are evergreen, then of course it's leaf on all year round. So even if it's a leaf off coverage, it'll give you the height of the trees and the underlying ground surface. But it will also give you maybe information on the distribution of rhododendron, gorse, these sort of things, evergreen species, even in the understory. So the combination of these two with species information and structure and height and number of layers is actually very important into the future and can be built in to your monitoring activities. So what I'm going to talk about now is how you can use those data to produce land cover and habitat maps. And we developed, the Earth observation data ecosystem monitoring with people who may be on the call. And that was developed over a long period of time. And what we've done is taken that forward to try and be much more detailed, and the idea that will then come back to everybody on their protected areas as well into the future. So that was done with the Eco Potential project, and yeah, we very much want to feed back into those protected areas where that was developed in the first place. So the way it works is early on we were just like tweaking indices, so you're looking at NDVI and so on to try and sort of classify a landscape, and so a point came a few years back where we thought, well, why don't we just take the actual forest and see if we can describe it using these environmental descriptors which have consistent units or categories. So the way you can see a forest, for example, you take these what is called primary descriptors, and so they would be things like canopy cover and canopy height. And canopy cover and height collectively would give you, say, life form, but the level, this is on the ground, so forget about the remote sensing for the minute. And then the leaf type and phenology and the stratification, how many layers and so on. So this basic classification is something you can do on the ground. So you've got your forest and you say, well, it's trees, they're closed canopy, they're tall, and they have they're broadleafed and they're deciduous, and they've got 2 layers. So you sort of end up with a sort of a legend a little bit like this. Now the next, you can also add on more information to them. So let's say we have, well, we know what the biomass is. We might say what the dominant species is. It might be European birch, the moisture content, leaf area index, and how much dead material there is. And so you have that initial description, plus you have this underneath it, which gives you details on that forest. So what we've done in Wales, and we've done a similar site, we've put it through the potential site as well, and we're expanding this all the time, is where we have a data website that looks at environmental descriptors on, it's called the Live in Wales website, and we'll give them the links to you later on in this presentation as well. So we thought, well, let's try and first of all build up all the descriptors that we know about in Wales or in Greece or wherever, and just list them all and see what's there. So we've got the website, it's wales.livingearth.online, and we've listed all the descriptors, how you measure them on the ground, and the remote sensing algorithms. So for example, we have woody biomass or leaf area index or herbaceous biomass. And if you come into here, it will tell you where you can get those data layers from. They won't be all the time. Some might be a kilometer resolution. Some might be there every 5 years. But it's a sort of a fairly up-to-date summary of what it is. And many of those are European as well. So if you go to the site, you'll see that you get access to the Copernicus layers and so on. So you have a large number of data sets, and then they may be from different sets and so on, but at least that information is there. And the key thing about those, we're looking for data sets of defined units if it's a continuous layer. So woody biomass would be tons per hectare, for example. It could be canopy cover percent or canopy height in meters. They should also have, or could also have, defined categories. So it could be a plant species. Leaf type is one, broad-leafed or needle-leafed and so on. So you have these categories, and the advantage of these units and categories is that I can apply them 1,000 years into the past, and I could apply them 1,000 years into the future, because a forest would still have 100 tons per biomass in 1,000 years time as it did have 2, 3, 4,000 years ago. So they're completely scalable. A plant species with a code of 10 would have a code of 10 100 years into the future, as long as you maintain that consistency. And that's one of the things to do, is to make sure that you have these consistent codes. Once you've got those, you can start to do some nice things. So what we've done is we've taken the Food and Agricultural Organization's land cover classification system, and it can be any system actually, but this is the one that we've used. And what we first do is find just 5 things. It's like going on a treasure hunt through your landscape, and it can be, if you can imagine your pot plant on your kitchen shelf, or you could imagine the whole of the Amazon rainforest. You can do 5 things. So first of all, you can find 5 things in the landscape. So the first thing is vegetation. So if I from my remote sensing data, I just find vegetation, I'll find the green, the dead, the submerged, or the bird vegetation. I just find the vegetation. All I have to do is do that. That's my only task. Once I've found that, I don't have to find the non-vegetated, because it's everything that is not vegetated. Okay, so this is this first level. So I found the vegetation. It's now everything else has to be not vegetated, which means I don't have to classify everything. I don't have to classify different roofs, color roofs, or roads, and it's just not vegetated. And so it makes your life a lot easier. The next thing you do is find what's water, whatever's easiest. And sometimes water is easier, sometimes it might be not water, but we find water is the easiest, and that includes anything that's wet. So you're looking at moisture indices. And so I sort of mentioned about the Sentinel time series. So you can take the Sentinel data and create a water measurement or indicator of water, open water, but also water and vegetation. Things like tassel cap wetness is another example. There's a number of ways of finding water. And then you summarize water. We do it over a year, for example, and say, well, if it's more than 12% water in a year, we'll call it aquatic. So we find anything that's aquatic, and anything that isn't aquatic is terrestrial. So we don't have to find the terrestrial, we just find the water. So all we're doing is finding 2 things, water and vegetation. And then what we then do is cross-tabulate it. So it's vegetated aquatic, vegetated terrestrial, non-vegetated aquatic, or non-vegetated terrestrial. So now we have a 4-class classification of images. Then we have to find 3 more things. We have to find the agricultural land. Now that's often, that depends on definition. So you have to make sure what you mean by cultivated land. You have to say, is a pine plantation cultivated? So as long as you define it, anybody can define it. As long as it's consistent over time, it's actually all right. But there are definitions with the FAO which we try to conform with. But it gets a bit common. Olive groves are a particularly difficult one as well, because are they cultivated? Are they semi-natural? If you find the cultivated, everything else has to be semi-natural or natural, and whether it's aquatic, terrestrial vegetation, or whether it's aquatic vegetated or terrestrial vegetated. And then if you come to this side, you then have the artificial, the artificial surface. So you find your urban areas. So anything that's like not vegetated, terrestrial, and is basically an urban or not an urban, it has to be a natural surface. So once you find your urban, anything else that's bare, in effect, has to be a naturally bare surface. You have to define that, and we use things like OpenStreetMap, master map. You can use existing layers, or you can do things like machine learning or deep learning. There's all sorts of ways of finding your urban areas, but you find sometimes they're easier to find than the naturally bare. Sometimes it's the other way around. So as long as you find one of those, it doesn't really matter. Then the artificial water or the natural water is the other thing you can find, and basically they're often there already. People know where they are, particularly in Europe, and so you can just say, well, anything that's not artificial, doesn't have a dam wall or whatever, it has to be a natural water. And what you end up is 8 categories. So you've got 8 categories in here. And you can also, I'll talk about this a bit later on, they don't have to be pure, but you say anything greater than 50% of that category, that pixel is going to be that. And that's quite a challenge to do that, but we've actually found it's actually relatively straightforward. And we get, in Wales, we get 96% accuracy on those 8 layers. Okay, 8 layers there. So these are the classes here. And then what we then do is say, well, actually, we can go, once we've got our vegetated, terrestrial, semi-natural vegetation, we can describe it in terms of cover, height, leaf type, phenology, and so on, and then life form, so it's trees. And like I said before, we can basically do this. So we do this as you do on the ground. We do it from space. So we find a canopy cover layer, a canopy height, leaf type, phenologies, and so on. Combine them together through this framework, provide more detail. So these are the layers we might look at. So we might have annual water, hydro period, and so on. And then we provide more descriptions of them. So it could be above ground biomass, it could be marine layers. So do coral reefs or any layer, you can do bathymetry. Doesn't matter what it is, land surface temperature, you just keep on building them up. So you end up with every pixel that's got a very detailed description, and it can come from anywhere. The only thing you've got to watch is obviously resolution, because often land surface temperature is maybe a 1 kilometer, but you've got a 10-meter sentinel image. So, you've got to try and marry them up. But generally, the land surface temperature is going to be pretty similar anyway across lots of 10-meter pixels. So generally, you're okay. The timing is important as well. So once you've got those, you can start to build up your land cover maps. So what we have here is images of the life form, so the layer for woody herbaceous with codes. There's a layer for broadleafed and needle-leafed and deciduous and evergreen, as they're all cross-tabulated. Then you've got your canopy cover, and then that's continuous layer from Copernicus split up into these layers here now. And then we've got biomass from CCI biomass, the ESA biomass map. And then we use those, combine them together to produce land cover maps. So these are the ones from Wales. They're available on wales.livingearth.online. And we'll give you that link at the end as well. And you can go and explore these. They're just, there's a whole explanation on there on the website, on the Geo portal. And you can see then 10-meter resolution maps of Wales. And you can add in layers. So you can add in, your biomass, you can add in your leaf type, whatever you want. And so the whole structure is there, but it's a different approach than before, where you might try to use machine learning to classify the whole landscape. This is built up of these different variables there. So we all we need to do now is focus on environmental descriptors. We don't need to classify the land cover because we're stacking everything together. We classify elements like veg, non-veg. Ideally, we try and use a biophysical unit, but we do use machine learning for urban, for example. Once you've got that, all you need to is just focus on the layers. So we've been focusing on dominant plant species. So this is the dominant species through Wales. And you've got ericoids and Molinia through here and so on, bracken here, and then the dominant crops. So the dominant, the semi-natural are from optical, the crops are from time series of radar, and you just put those together, and then we can get what's the biomass of the forest, what's the herbaceous biomass of the crops, how much dead material is in the bracken, what's the flowering times of the ericoids, or what's the wetness of the bog. So we just focus on different things of this our landscape. What's the depth of the water? How turbid is it? And so on. So you can use this combination. So you don't have, the classification is completely automatic, puts those together. We've developed it more for Wales, and it means that then we've developed it also in conjunction with national parks in Europe as well. We brought that together, and then the idea is then to push that back to everybody. So you can actually do this for locations in Europe as well. And I'll show you how we're doing that as well. So the accuracy is really important. So at the minute we're using, what about 96% accurate for the level 3, which is pretty good. We find the accuracy is better than if you just try and classify the landscape through, say, supervised training. But we do use classification in that procedure. These are validated by aerial photography, but we're looking at deep learning approaches on aerial photography as well to try and automate that approach. And we've also developed what we call the EarthTrack mobile application, which exactly replicates the land cover. So here we've got the level 3 land covers, the 8 class I talked about. Here they are around Aberystwyth, and we've got sites through Europe, down through Asia, a lot through Australia, and a few in South America. But this is openly on the download. You can download the app and you can download the data for no cost, as we can with the maps. I'll explain why we do that in a sec. You can go and collect a point. I can go outside, collect a point now, and it'll be available since 2018. Any point I collect will be available within a couple of minutes, and it means you can validate the land cover maps in exactly the same way. So we record canopy cover, canopy height, and so on. The advantage of that is that that legend here on these points exactly matches the legend on our level 3 and our more detailed classification. So you connect that description on the ground with what you connect from space. So you're basically doing the same thing, which makes it really understandable. It means that, you know, if somebody's on the ground, they can see how tall a forest is, what the cover is, what the species is. We can do the same from satellite. It's just they have different levels of uncertainty, but it's the same process. So whatever you record, every time you press the button on the app, you're validating the maps. So I'll stop there just for a minute because we're going to change. But yeah, any questions? Otherwise, I'll just carry on then.
We cannot see any questions in Q&A, but maybe somebody would like to ask it now, having something in mind. Or also we can raise your hand and we can allow you to talk. Not now? Okay, so I think, Richard, that we can carry on and we'll wait for the questions.
Okay, yeah, no, that's fine. So it's quite a lot to take in as well. So, and I'd say there's a bit more to take in the next sections, but hopefully I'll try and make it as straightforward as possible. As well as land cover, you can also do change with the mobile app. So what we have here is points in red and green, and basically the green points are sort of good things that happen ecologically, for example, and the red are not so good things like damage because of climate. The blue is a flood, and so on. So we've got at the minute like 8 categories, but we're going to put those into a much larger range of categories, and I'll explain how that will be. And that's sort of just finishing that work up now. And that will mean that you've got the ability to go onto the ground, and if you see something happen, you can report it immediately through EarthTrack, and it means that it'll flash up here, so everybody would know what's happened. So we had a cliff fall the other week, and you just put it in straight away. There's a photograph, looking up, looking down, and so on, a full LCCS description, and so on. I should also point out now that the land cover classification systems work we've done with Palmer Blonder and others before in Biosos, where you can actually translate the land LCCS to, say, a habitat classification, so a taxonomy. So we're trying to translate these to the phase 1 in the UK and other habitats as well. So it is the best direct link with habitat. So if we look at describing and quantifying change, basically I'm going to go through the mechanism for doing that. So what we have here is we have our land classifications constructed from environmental descriptors, and they've got predefined units, meters, percent, or time is also included in there, or categories, say life form, leaf type, or species. But note the LCCS does not include species at this point. It's like an additional descriptor. So if we take our level 3, we've defined our 8 classes at level 3. And so we end up with 64 classes here. And then what we then have is effectively a matrix of change. So it's like the same as the IPCC matrices of change. So anything that's so you've got 8 here, time 1, 8 here, times 2. So you've got 64 change classes in here. And those 64 change classes, about obviously they're these going across from one to another. So you get natural terrestrial vegetation to a bare surface is an extent change. Anything that's along the diagonal is an amount, a type, or a type change. So amount, condition, or type change. And when we mean condition, Clive will know about this. We're talking about things like biophysical, things like health, chemistry, biology, or physical measures like turbidity or biomass is an amount change. So a health change would be turbidity or chlorophyll amounts and so on. So those are the three things that happen down here. This is definitely an extent change. And we also include woody and herbaceous because that's what the IPCC looks at. So woody herbaceous vegetation, goes woody to herbaceous or herbaceous to woody, or it stays as woody and the biomass goes up, biomass goes down, or the crown cover goes up or down, or the foliar chemistry changes, for example. So we've got our description there. So what the first thing we do is look at what we observe, the observed change. This is Australia, for example. We've gone here. This is actually the Harbour Bridge and Sydney Opera House. And you can see then we've got an increase in here, which you'll see a bit later on, is an increase in the extent of natural terrestrial vegetation in a city. It's actually correct. They've put a new park there with entirely native species there. So that's our increase in natural terrestrial vegetation, although it is effectively parkland, but we can describe that later. But it's what we observe. Here we observe a loss of mangrove extent in natural aquatic vegetation. So we've sort of lost that because of a big dieback event. Here we've lost photosynthetic vegetation in Hinchinbrook Island on the Queensland coast because of Cyclone Yasi in 2011. So we've been able to put this classification through these sites in Australia, look at the change in here, whether it's an extent or a conditional type change, and that's just what we observe. So we're not making any conclusions about that, it's just what we're observing. Okay.
May I interrupt you, Richard, because we've got a question from audience?
Yeah.
Okay, so there's a question asked by Konstantinos Perikleous. I have a question regarding the recognition of species of trees and plants. Can you recognize through aerial or satellite images a species of tree or plant based on the color of its blossoms?
Yes, so there's lots of new things coming up with that. So it depends on the species, to be honest. We've been doing some work with Sentinel and so on. So if you've got like, there's lots of ammunition there available for you. And again, I'll explain this a bit later on. So you could have like just a spectral response, like the red edge of superdoves or the Sentinel-2, this red edge band, which Landsat didn't have, gives you much better discrimination, but you get better discrimination in October for trees as opposed to March is quite good, but July and December are not very good at all. So the discrimination is quite good on those transition periods. The other thing you could do, if you could pick up the leafing, the timing of leaf start, leaf end, or the length of leafing, they're all standard measures. And so those standard measures they've got units or categories, so they can be compared as well. So you've got a whole range of different things, as well as things like structure. So you know that rhododendron doesn't get more than 20 foot, or let's say 6 meters in height. So if they've got a tree that's got the same spectral response as rhododendron from, say, the LiDAR, and it's 35 meters, it's not rhododendron. So it's like there's all sorts of ways of doing it, and there's new tools. So there's a good literature. So it depends on whether you're using drones or airborne or Planet or Sentinel. It depends on what you're looking at. But in this system, what we say is that this might be dominated by oak. It's a pine actually, but we say it's dominated by oak, but it's co-dominated by another species, and the dominant in the understory is rhododendron. So you can still, that whole system works through here. So we can say, well, this has been cleared, this forest has been cleared, it was a pine, it had a second layer and it had rhododendron in it, whatever. You can do all sorts of things in there. I don't know if that answers, that's quite a long answer for you, but hopefully it helps.
Thank you,
Where
Richard.
there's a will, there's a way.
No more questions for now. Thank you.
So what we do, taking this interaction then, we've got our changes. So here we've got a change in the plantation clearing I'm going to show you before. You've got we'll call it a natural forest here. So it's got a natural forest and it's moved into a bare area. So that's one type of change. But a forest, it might stay the same. Yeah, it might stay as a natural vegetation because it could be grassland. So it's still, it's what's changed is the life form. So we can come down here and say, well, it's changed from woody to herbaceous. So it could be from woody, veg to bare, but it also could be woody to herbaceous. And so what this does, this combination here, these red areas are both. So there's an extent change in a major category, but there's also, it's still vegetation, but it's a life form change. So what we do is build up this continual accumulation of evidence to work out what it is. So it might be that the forest stays the same, but the canopy cover, like this regrowth, increases. It's still forest. And so you're not, if you go from here to here, it's regrowth. But even if it's got an increase in canopy cover, it's still regrowth forest. So there's two ways of describing regrowth. And there might be more. The canopy cover might stay at 50%, but the height increases. And so it's still natural vegetation, still got a cover the same, still stays the same, but the height increases. So it's all that evidence is built up, and that allows you to map the landscape much, much better. So here, for example, we've got, this is our original classification. So we've compared the level 3 and the example I gave you before, these here plus 2 life form categories. And then now what we then can do is compare much more detail. So all the components of the land cover, which is thousands of classes, are individually compared. So we can say trees that are this tall to graminoids or forbs to this tall. You've got a complete matrix of all of these all in there, which means that then if you get a change in anything like canopy cover, height and so on, it's all calculated through. So my original class goes from here. It's got a second layer. It's got a biomass of 210. Got eucalyptus in here. It's got this canopy cover and this height. But after, say, a fire, it goes from close to sparse. The canopy cover goes from 70 to 60 to 20. The height stays the same because the fire hasn't actually destroyed the forest enough to bring the height category down. It'd still be continuous and broadleaf evergreen, but it's got no second layer anymore. The other second layer is gone. The biomass has gone down as well, and then it's dominated by the same species. So some things are changing, some things are not. Some things are changing by a certain amount, and other things aren't. So that combination then creates an alert of change, and we build that evidence to say, well, that's a vegetation damage because of a wildfire. So we look for the causes, the impact, and what caused it. And so that's what we put through. So, for example, if we go for Australia, I've got a couple of examples for Australia at the top. So we've got dieback because of storms. If you look at the third one along, you've got dieback because of sea level drop, but the dieback is still dieback, and it would still be mapped as dieback. But what we're bringing in is other information to say, oh, there was a storm yesterday, so it's quite obvious that the dieback is because of a storm, or the damage is because of a storm. Whereas sea level, here we've got a sea level drop. Again, it's dieback. Now, this dieback from the storm could have been quite severe, so you could get damage and dieback. So you can sort of string these things together. Here we've got dieback because of pathogens, which would look like effectively like that. How do you know? It could be what's the difference between that one and that one? And then dieback because of a bushfire. Well, you've got a burn scar with this one, so that's another clue. And you can see it on the ground, you see. So earth track does the same. Vegetation damage because of a storm. So that one would go with, say, that one, and then dieback with that one. Although that's Australia, that's Wales. But it shows it's globally applicable. So your evidence are quite interesting. You've got impacts and pressures. Source of information vary. Time is an important determination of change, and that goes from days to decades. And you can get changes can be positive. So if you're restoring an area, then it can still be, increase or restoration, or increase in vegetation amount because of restoration. So that's what that would do for you there. So yeah, I'll stop again there. If there's any questions on that. So the idea is basically our mapping is based on environmental descriptors, and our change is based on evidence, on comparing those descriptors.
I cannot see any more questions, but perhaps somebody would like to speak something. Please just raise your hand and I will allow you to speak. Nobody for now. Last chance to ask it live.
That's okay.
Oh, sorry. I can see a question. Yeah, there's one. A lot of examples are woodland. How useful is it on grassland habitats?
Yeah, it's exactly the same. We use woodland because there's more descriptors in effect in woodland. It's the easier. It's a better way of illustrating something. It would work for anything. So you could do like a glacier. You could do a grassland. You could do a bog. You just retrieve the things that are important. So for grassland might be it would be the cover. You can still do a height of a grassland. Whether you can pick it up from satellite it's not impossible, it's more difficult, but you can indicate height. Leaf area index, you use different algorithms. So you just take the algorithms from different places and put those together. For bogs, you might use moisture content. Peak depth, you can bring in other information. So we brought in peak depth. Yeah, you just have to look at the environment and describe it how you would describe it on the ground, and see, can I pick that up from satellite or aircraft? And if you can't, accept you can't. But if there's any way you can, then go for it, really. See what you take the best one. It might not be as reliable, but then it shows you where to improve. So I'll improve my grass height classification by finding an algorithm that really does grass height and use the best one. So it can be different. In Wales, we're looking for national algorithms, as in, we're trying to make consistent. What's nice about this system, though, as we demonstrate eco-potential, is that it would work across national parks or any protected areas. So you have a consistent and comparable taxonomy, and you can use the same algorithms, for the same biomass algorithm is the one for Wales comes from the global map, basically. So you can do it that way. So yes, you can describe anything.
Yeah, and we've got two more questions. First one was asked by Evelyn Underwood. Do you have any estimates of how much applying these procedures would cost for protected area managers?
I think one thing that's useful about this is that, we could apply it to Snowdonia National Park in Wales, for example. So the option here is to do it nationally, so that everybody who has a protected area in Wales has got, as the bare minimum, a national algorithm. So it needs to be applying north and south of Wales, for example, or north, east and west of Austria. As long as it's a consistent one, a national one is really good. So things like the Slovenian national coverage would be really good for LiDAR. So that would give you a consistent layer. So it needs, that's where Eurosight would be really good to try and talk through how best to, what is the best algorithm. Another useful thing here is that if you have canopy cover and you take the Copernicus one, which we've done, it's pretty good, but there are ways to improve it. So maybe we could take one from Matt Hansen in the United States, the global one, and use that. But we need to know how good it is. And so what we're focusing on is not really creating an algorithm, but working out how good are the ones we've got. So you need a common ground data set, which is like Earth track and other things. So we're trying to make standardized measurements from drones or whatever is ground truth. And then you can make an assessment of how to improve that. And if you feel that you need to have a canopy cover algorithm your own, then it's best to say, well, why don't we link up with other protected areas, either in our country or through Europe or the world, and come up with the best algorithm that works everywhere. And you might have variations of it. So we use the global biomass algorithm, but we're testing it in Wales. So we're seeing how good it is. And if it's not good enough, then we can work with ESA to say, well, let's try and improve it because it doesn't work very well in Wales. We did that a long time ago with the Australia. We released 27,000 plots of biomass data, and that's been used for biomass, validating global biomass products for years now, because it's an open, free data set and people can test how good it is. And I think that's the way to go forward, really. So hopefully that does answer a little bit for you.
Yes, thank you. And the next question is from Tom Spanhoff. Do you include classification uncertainty in the environmental descriptors to determine the type of change?
Yes. So what happens, every layer needs to have an uncertainty associated with it. So the biomass one, it's a prerequisite of many of the Easter ones to have uncertainty attached to it. So, everything, if you need to account for that. And it gets complicated then pushing it all together. But at least you know if it's uncertain. And there's a good example is that mangrove example in the here. So that dieback affected, hundreds of thousands of hectares of, or tens of thousands of hectares of mangroves up in the north of Australia. And so if that just been like a 30% reduction in canopy cover, would that have prompted a response? And the answer is probably not. If you went to 50%, would the response be bigger? Yeah, maybe slightly, but if it's all gone, which it did, then there was like, international news press and so on, and then they put a monitoring system in place and so on. So the percent, the impact or the degree of impact determines the response. But if you have a 30% loss, but actually it's inaccurate by say 50%, at what point do you start to say you need to do something about it? So quantifying the uncertainty is really critical. And every layer needs to have it. So spatially, you have a plus or minus what it is as well.
And another question, and greetings from Alan Brown. And the question is, I can understand how we are using evidence for changes in life forms and how detected change can be validated on the ground. How confident are you in detecting changes in condition, some of which might be observed on the ground, but may not be signaled in environmental descriptors? In other words, what do we have to say about those parts of the map which show no apparent changes, and as a statistical data layer?
Yeah, and that's an interesting one. So looking at change, there's a couple of things. So there's this lag. So like you might get changes from disease of plants. They might not appear, the disease might be there for a year. It won't appear until you suddenly get this big dieback. So there's a lag in your change, so you won't pick it up. For regrowth of forests, say in the Amazon or anywhere, the Amazon is a good example, where your forest is only visible, a regrowth forest, for 25 years next to a primary forest. So it's only visible for 25 years, but it's still growing. So you've got height. So you might want to bring in things like the Jedi LiDAR and other things there to sort of bring in more evidence, or the number of layers. The biomass is a really good example of the longer term. So optically, it doesn't look the same. But the different wavelengths, you can use that. And the other thing is the wavelength for picking up in the first place. If you plant mangroves, if you planted mangrove trees on mudflats, for example, or you would pick them up straight away if they're like a meter high. You'd pick them up from X-band radar. You wouldn't see them from C-band or L-band or P-band until like 5, 10, 20 years time respectively, until they get big enough. So the change, the manifestation, the lags, and the total period is considered as part of the evidence. So it's complicated, but it's actually also quite simple as well. So you've got to get that balance, really.
I really like you saying that it's complicated but quite simple. Thanks, Richard.
You can make it complicated, and then you don't get anywhere, or you can make it simple and try and get somewhere that way. I think that's the approach.
At least it's simple for you, not for all of us. And the last question in this session, this question session of questions, not the webinar. Another question from Evelyn. Is it possible to set up an automated alert system that will warn of possibility damaging land use changes in your area of interest, so that you can go in and investigate it?
Yes, that's the idea. So what we're doing in Wales the next couple of years now, we're going to be setting up alerts of change, and the EarthTrack mobile app, which we'll make a professional version, which is applicable outside of Wales. You can go there and you can record it straight away. So, obviously, things like Planet is ideal, but Sentinel, annual changes are the most obvious ones for lots of people. But if you get a fire and you want to monitor anything, you need to have people there all the time. And that's where I think the EarthTrack is really useful. Yeah, so the idea is a near real-time alert. You use your evidence to say what it is, what the impact, what's the cause of it, and then you go with the app and you do the same, or you use drones. It's completely scalable in space and time, the approach we're presenting here. And it also encourages a lot of collaboration. So the Wales maps are produced, you can see from Copernicus, ESA, forest research. It's all very collaborative and all open.
Thank you. So I can't see any more questions for now, so you can proceed with your presentation.
Okay, that's great. Hopefully it makes sense as well. So what I want to do now is this is a presentation we gave a couple of weeks. It's slightly modified, but I really wanted to show it to you because I think it's important, particularly given all the changes that are happening at the minute. So what I'm going to look at positive change. So rather than just looking at change, like that has happened in the past, we want to sort of look at ways of going forward for conservation, restoration, and sustainable use. So, for decades, we've lost and degraded the environment. I think most of us on the call didn't want that to happen. And the reason why we know of things that are happening all over the place is because of, what's happening in Earth observation. So we're sort of seeing, this was provided by Planet, you can sort of see, the loss of the forest, the loss of the glaciers, mining, the Owl Sea, and so on. So you're always seeing what's happened and what's been lost and what's been degraded. So the majority of studies have really looked at the past impacts rather than solutions for the future. So if I now change that and I say, well, why don't we reverse it and then take that back to forest? That would be quite nice to see, and I'm sure you would like to see that as well. So if we could get our glaciers back, if we get the Owl Sea back to what it was, we can rehabilitate mines, get some of the agricultural fields back. Maybe that was a dam. You don't want to drain the dam. You want to keep maintaining your infrastructure, but you also need to restore things like mines. And so I'm just going to sort of put some ideas forward and how this approach we've been showing you can be used for that. So first thing you do is use the past and the present to inform what's going to happen into the future. You can provide quantitative descriptors of what you think would be the future, what you want. You just say, I want to have this. Okay. Then you can agree and set targets and values, and then monitor progress towards those targets, and then quantify and understand what's happening on the ground and make sure that what you're trying to achieve is being achieved. So, first of all, using the past and present to inform the future. What we've done with Clive is in Wales and it's based on a lot of work we were doing in Australia. So before the Europeans arrived in Australia, the ecosystems were pretty intact, although affected by indigenous fires. But they know what the ecosystem was basically looking like. So what we did with Clive is work out in Wales what the effectively the best, what they call them, reference ecosystems are in Wales. And so it could be a sessile oak woodland, or it could be a blanket bulb, or whatever. It's a reference ecosystem where, if you took everything out, that was what it would look like. So what we try to do is make people aware. It's on the Living Wales website. The website is listed here. It's trying to say, well, this is what, if there's no interference, it would look like this. And then if it's modified, it might be grazed by sheep, or it could be, plant, lots of different ways it's been modified. It could have been drained and so on. So the modified and reference states are all listed there. And that's really to try and give people an idea of, what are you aiming for? What do we want to get? And you might not want that reference state. You might want something else for biodiversity, for example. The other thing is to look at the forest maps back 8,000 years ago and say, well, where was the forest areas? It's massive in Africa and through here. It's interesting to look at Australia, and it's just like there was a lot of forest that's been cleared, but actually you think it was a lot more forest than it actually was. So these are sort of things that are quite interesting to look at. So by looking at the past and sort of trying to get an idea of what was there to start with, and also then what you might be able to get back to, would be quite interesting. So what we find in Wales is there's lots of isolated trees all through the landscape, which are like a metre diameter, a metre and a half, and they're often on farmland. You see them in the valleys and so on, and you realise that actually there's potential for a really big biomass forest in parts of Wales, as an example, or a really good large amount of so I'll just get rid of that one. A large amount of blanket bog or something with peat in there. So that's what you've got there. So you've got these reference systems, and then so knowing what's there before is quite useful. The other one then is the is to use the time series of satellite data. So from Australia and also Google Earth Engine, you look back in time, and you can see then what happened in, say, 1984 to 2020. You can classify the land cover like here, and you can see what it used to be like. So this is like 2020, but this is what it used to be like in 1984. This is in June in Queensland in this point. And you can say, well, maybe I could restore this back to this one. So knowing the past is really important, but it also tells you the probabilities of events and processes like fire or flood frequency to understand sort of states and transitions. So for example, we tell how often there's been a flood, how often there's been a fire, and so that helps you in the future to say, well, if I plant something here, is it going to burn down in 10 years' time? So we found out the mangrove dieback actually happens every 18 years. There's always a mangrove dieback, it's natural. So, you know, by knowing that tells you, well, if I'm going to restore mangroves, they're going to die back in 18 years' time anyway. So, but don't worry about it. But if there's, you know, if something does happen, which is out of the ordinary, at least you've got some idea it would happen. With the potential, we'll also put this virtual laboratory as well, put in to sort of look at how you can sort of anywhere in the world to look at changes, how they're happening and the impacts of those like fires and so on. So using the past is quite important as well. The other one is to identify and illustrate tipping points. So for example, the mangrove dieback or coral bleaching or something like that will tell us that actually this transformed that ecosystem. So let's say this mangrove didn't recover. What do they go to? Do they go back as salt marsh or what do they, or mud flats? So after that dieback, they had cyclones, had sea level, further sea level changes, and also big floods. And so that was happening there. And then also, so if you restore, you need to know, you know, is that tipped? So is it gone to Molinia grass and in the UK now? Is that it? And the other thing is, like, can you actually get areas back, like Sydney? Can you really restore that? And the answer is no. But you can still restore the national park I was talking about. So that's coming back quite nicely to see that as well. So the other thing is then just to use the past and present to inform the future. So we look at Earth observation case studies, and we can sort of say, well, you know, actually what happened with this event? What happened to that fire in Brazil? What happened to that flood? Is that left a wetland because it happens so often now? You know, how often was it, you know, what was the dieback because of I dammed something? What was the impact on the vegetation? You learn about what's happening by looking back in the past and look at barriers to restoration and actually discuss things as you go forward. So you say vegetation loss happened because of deforestation of sugarcane in the Andes, but then crop were established and they were planting, so you got crop establishment. And then am I going to replant this to come back to forest? So you can sort of track things and see what happened and what was a success and what wasn't. So that's another way of using satellite data. Now, what's interesting is because we've used environmental descriptors, we can actually use that time series to map things and describe things like fire frequency, canopy cover, and so on. But also, can we then use that to inform things like state and transition models, which help you understand, their spatial models help you understand how certain ecosystems transition into others. You could use models that predict like hydro period of water, growth of plants, colonization, species invasion. So the species distribution models tell you how rhododendron might spread through a landscape or how pathogens might do that as well. And again, you can use satellite data to initiate these models. So we now know that actually, although that's a leaf off coverage, all of that is forest. We know the species from planet. So we can say, well, if this forest is, you know, a pine or it's an oak or whatever, we know the species, we know the height. We can say, well, the biomass rate of a 50-year-old forest is much, much lower than it would be, you know, for a 10-year-old forest. So we can start to, you know, look at modeling and how that could change as well. And then, so there's all those tools that you can use. And there's also lots of initiatives now at restoring landscapes. So Sustainable Development Goals, the Decade of Restoration, Global Mangrove Watch, you know, they're saying, you know, we want to expand the area of mangroves by 20% by the year 2030. And all the National Forest of Wales wants to restore forests into here. The question is, like, how do you need to sort of say, where are those forests being planted? Where's that ecosystem restoration happening? And so in Living Wales, try to sort of make it sort of much more open to sort of see, well, can we sort of show where that's happening, and then to track it over time, but also to give values to those ecosystems. So as you restore forest here, so for example, this is the land cover map for Wales, and there's a little bit of area in here, which is an opportunity for forestry, or some in here, we could have like a bog area if you want to restore that. But you've got a target, you've got all the variables that you can predict those variables to create the future land cover map. So you can do exactly what we did with land cover mapping, but use predictions of those variables to create a future map. So we could say, I use forest as an example, but it could be anything. So this forest here in the green can then be inserted into here. And you can say in 50 years time, I expect this height, this cover, and so on. And this is how I'm going to make progress towards it. This is my plan. Make the plan available, and then you can monitor the plan from satellite data. But if you could actually attribute the variables with values, like financial values or something, so it makes it viable, but allow for agriculture and forestry, so there's competing requirements for the landscape. So try and have a plan within that. This sort of system allows you to do that. So another way is to try and get the accounting in to restore natural capital, and to try and link that into other economics, and link it into what you know from the landscape in the past, what it could be in the future, and sort of try and prepare people with what might be, and say what the benefits would be into the future. So for Wales, we're looking at improving then the monitoring of EDs, environmental descriptors, through the future, with concentrating on macroalgae, turbidity measures, snow cover, plant species. And then we're monitoring those, trying to set up a system for monitoring into the future, but then to allow that to come back into other places so it could be used in Europe as well. And so that's the idea, and to try and bring it into habitat taxonomies. And so the idea is to try and really sort of build up a plan for the future, or try and show how that could be done. And I'm sure it links into lots of existing programs. So last couple of slides is then, it'd be really quite good if people would say restoring bogs or looking at grasslands or whatever, or coastal habitats. If you had a mobile app like we have with EarthTrack that sort of shows, this people collectively. So let's say all the people in yellow were planting, forests back, or the people in green are looking at grasslands or whatever. You have you have photographs of that event happening over the next 10 to 20 years. You could actually show and share what's happening going forward. And so are those plans you put in place, and is the financial rewards and so on, are they being realized? And you're using satellite data to do that, as well as the ground. So you're connecting then people on the ground with what's happening from the satellite. So it's quite nice to try and link in here. So we're looking at defining change. What is happening? Is it positive? Is it negative? Is my plantation or my restoration project going well? The algorithms or models that I'm developing, do we need to develop those, and how reliable they are? So ground truthing is really good for testing how reliable my canopy cover map might be, for example, whether I've got bird species coming back into my forest. They're obviously very useful for validating land cover and change maps. You've got citizen science. Associated land covers with distribution of flora and fauna. Am I returning my wading birds to the uplands? What's happening when I put that plan in place? Is it actually having an impact on the flora and fauna? It's really important to involve lots of people on that, and I think that's why the Living Wales maps are open, to sort of show people how what the landscape looks like now, what could be achieved. We're not saying what you should do, but just saying those are the options, really. And the approach we're taking is global, but it's sort of locally relevant. So that's the idea behind it. The last bit then is just, we feel that proactive engagement involvement is really critical. So one thing we've been doing is working with the Centre for Alternative Technology in near Maculleth, near here. It's almost a tourist resort, but it's an educational centre as well. And we put all the maps and the EarthTrack points and everything into that centre. So when people visit, tourists and so on, they get an idea of what's happening in Wales, where the forest clearings are, how they can contribute, what's the plan, and so on. So that's the idea behind it. So trying to get that case of where things are happening and how the public and stakeholders can be involved in helping to make positive change. And that's through thinking portals, websites like Clive did with the future, the different ecosystems and just general social media. So it is actually really nice. And if anybody's interested, we do have a mobile exhibition which can show this, and it could be taken other places as well, International Park headquarters and so on, just to show what's happening in the world and how it's being changed in a positive way. So finally, conclusion, there's several emerging tools and approaches that, that are being used using Earth observation. So I think we've hopefully presented an example where we think it's working really well. It's involving a lot of technologies such as the Potential Virtual Laboratory, Open Data Cubes, Google Earth Engine. We have things like the Land Cover Classification System, the LCCS, and a change taxonomy. We're developing frameworks to generate consistent products over space and time. And that means that they apply in Wales, but anywhere in the world, we're trying to make it so it's applicable and usable. And there's significant potential to plan and predict future landscapes through, looking at EO-derived products and models. We can bring those in and sort of say, well, what would you like? How do we get there? What's the economic problem with that, or the benefits and so on? That would be really good. So I think combining these technologies provide, significant capacity to actually shape future landscapes and not look at the past all the time, but to say, let's go forward. We know that use the past to inform going forward. And this mechanism of linking environmental descriptors through the whole thing is really powerful, and we feel it works really well. So that's it really. So there's lots of people who've been involved. All the potential people that's been in Australia and the US and so on. There's so many people to thank. But I hopefully what I've been talking about is useful. Would love to have your feedback, and if you're interested, just let us know as well.
Thanks a lot, Richard. It was a very intensive and great journey through Australia and Wales, and very global. And I would say that I like especially one of your sentences that is globally applicable but locally relevant. So I think we can use it as promotion for our Euroscience network and our working group as well, because it's very relevant to all our activities in Euroscience. So I really like it. And we still have 15 minutes for the final discussion. So I would propose, I hope you don't mind that, because I can see in our audience some members of our working group. So I would like to promote them to panelists. But so please, if you wouldn't like us to see you, please switch off your camera. So I will try to promote some colleagues that I can see here. So also all attendees will be able to see more people from our group and to have maybe a kind of a panel discussion about the issues raised by Richard. So okay, so I'm trying to do that. So please join. Looking for our friends.
I'll just stop sharing there, Volchek.
Yes, please. You can also leave for a minute this nice picture. It's okay. And we will see our colleagues here soon. I see also speakers for next webinar, so they can say a few words about next meetings as well. Just a moment. It's not that easy, but okay. I think. Okay, I think that it's done. So, okay, I think that now you can stop sharing your screen, Richard. And great, so you can see quite a lot of our colleagues are here. And are there any first-hand comments about the webinar, about the issues that we are talking about from our colleagues? I know that you are not prepared. It was a surprise to take you here, but, I hope.
Can I pick up a couple of things? Partly, in relation to Evelyn's question to do with alerts. Obviously, have an alert when something has changed is something that we would all like to have. The degree, I mean, the problem with it is really how much change would you like to see before you're alerted about it, I guess. Because you don't want to be alerted at sort of minor changes and things like this that would happen on a daily basis. So how much of a change would have to happen in order for you to be alerted? And I think that's the problem with the alert thing. The potential is there to do it. I think it is, and like I say, it's something that's probably every person working in conservation would like to have. And then the second thing I was going to pick up was the question from Toon, which was to do with the uncertainty thing. Is that we're currently looking or trying at least to get or at least to express the different levels of uncertainty with the different types of sensor, basically, and linking that to the environmental variables. So that's a piece of work that we're currently engaged on now. So yeah, we're definitely sort of trying to take that into account at the same time. So they're the two things I wanted to pick up, because I don't think Richard heard the question about the alerts.
And what we find is with the alerts that happen, you pick up quite a lot of them, but they actually find them quite clustered often, particularly at higher resolution. And you sort of, it first of all indicates you where something's happening, so you can go and look a bit more. But as your environmental descriptors improve, so does your alerts. So, some are better than others, but, some are obviously due to errors, but, they do work. It's an automated approach to doing it. So.
Yeah, the problem is how many alerts do you want, isn't it? I mean, simply because things are changing all the time. So.
The other thing is, I think Alan is mentioning about environmental descriptors. Again, it's the confidence in those descriptors. It's like, everything has got errors with it. It's never 100%, but it gives you a record over time, and you can sort of track something, because some of these changes can take place over decades. And so what you're looking at is time. Depends on how you pick it up. Depends on lots of things. Like a flash flood, you're going to miss. You're not going to see a flash flood most of the time, unless you're lucky. So the time dimension is very important as well. But certainly, condition changes and amounts and so on. Yeah, you can definitely see them, but it's putting them into a framework which really hasn't. It's quite difficult to do that. So hopefully, this is providing a mechanism for doing that.
Shall I say something in response? So hi, Richard. I thought this is really interesting. I think I just wanted to say that it's nice that things have clearly moved on from where we had to work with habitat classifications, and I think there's probably across Europe there's going to be a very nice and interesting period where we reconcile the information that we've got that's often bundled up in classification terms with these new ways of working. The main point I was behind my question was, I guess as nature conservationists, we're aware that sometimes the really important changes are happening not only slowly, but very subtly. Particularly the losses of rare species where there's no real corresponding changes in cover. And of course, remote sensing is mainly picking up the cover forming or dominant species. And what I was thinking, two things. The first is that over time, we'll get a better idea of which changes are detectable. And I guess it will allow us to then sometimes build backwards to find those points where the changes might have been detected as early as possible. Then that can feed into the sorts of things that people are looking for on the ground. Now, what interests me is whether eventually the structure of changes in the environmental variables, so not only the habitat, the land cover and habitat, but also the patterns of change could then be used to stratify some sort of paid for surveillance system that started to look in those places where people weren't necessarily noticing change, but change might be taking place. So in other words, as well as what you have, which is very much an alert system that's triggered by people noticing things and then making observations, that there needs to be some sort of complementary filling in, so to speak, of repeated observations in places where we think change might be taking place, and that can be statistically linked in with the living whales, so to speak, the analysis that gets better and better and better over time as it's informed by new sensors, but also by the ground observations. So it's
the
really
idea behind the change, Alan, is that when you see a change, you might be monitoring an area and nobody goes to it, but when you do see a change, something starts to appear, you can go there and direct ground observations, but then that feeds into when you're collecting data on the ground, it feeds into your algorithm. So your ability to detect change, if I want to detect wind throw in Wales, I have no idea because there's no ground truth. Now there is. So, but the more of it, then the better your algorithm will be, particularly if you're retrieving the variable. So it allows everybody to sort of contribute to it. So the points for Wales are collected by lots and lots of people, and it's going to increase, and it becomes part of a routine that people will automatically take a point because it's useful. And it is, it's really useful for that. So.
And again, in the past, essentially land cover and land cover change was something that was developed centrally and then sort of dished out to all the users and practitioners. But now we've got something where everybody can participate, and that means that there's much more confidence in the system as well going forward. I think that's great.
And that's a way forward for maybe for your side as well, checking out the people listening, is that what we find is that certainly here and say in Australia and other places around the world, is that it's a common language because it's environmental descriptors. Everybody knows what tree height is, so it's all common. So it's not, everybody can understand it, but also collectively we can collect data from North South Wales and have a campaign. So have a canopy cover campaign. So 2,000 measures of canopy cover last July. And so we can test the algorithms for canopy covers and do a snow cover campaign. So throughout protected areas, you can have a campaign for doing that, but it needs to be developed on a finer level. But it would work for anywhere. And we are developing capacity so it comes back in to the potential sites as a minimum, but then going through to others. So if there's interest, but I think Eurosite would be a really good place to coordinate that as well.
One of the key things here, I think, is the use of the apps. So like EarthTrack to actually, just through the EarthTrack recordings that have been done so far, we've got photographs of so many places we didn't have photographs of before that we can revisit in 20 years' time because we've got the grid references, we know which field it was, and just by the public going out and taking photographs, if you can engage, you've not only got a validation tool for the remote sensing, you've got this ability, as Alan was saying, to actually see how changes have happened in the future on the ground, just from simple photographs taken through a phone app. And I think this stuff, it all comes together really well, but it's building to the future really. But they're the things we'll learn from.
It would be interesting to encourage people to take vertical photographs of the ground cover.
Yes, they do that, the vertical, and we would do the 360, the 4 photographs. That's the plan. But there is a new version coming up. We're trying to get that out so that then you can use it as well. And then it also supports algorithms, so if there's an algorithm for Europe, say on canopy cover, like the Copernicus, how good is it, for example, or whatever. And then, how does it work in Wales as well? And we say, well, it really works in the north of Spain. But so why isn't it working in Wales? So it's actually useful having information beyond Wales or even globally to sort of try and support that. And I know people at ESA and so on can use that for land cover maps and so on. So it will contribute. It's all open and available as well, by the way. So.
It sounds as though what will come out of this then would be also a sort of European stratification by geography. So in other words, once you start to know the scope, the spatial geographical scope of some of the algorithms, you'll get a much better idea of what compares with what. So if you've got changes in one place, then what else is like that, and where else might be changing like that? Interesting, isn't it?
But I say having that restoration future or that plan is if you're working towards that, it all makes everything a lot more worthwhile too. So.
Okay. Just a reminder that you can still write your questions in Q&A or in chat, or you can raise your hand to speak. If there is anybody, perhaps somebody from our panelists would like to add something. Are there any volunteers? Okay. No more question. I'm just checking our Q&A and chat. No, I cannot see more questions. Well, we are just about last 4 minutes to finish our webinar. I cannot see any more questions. So, if you would like to ask some questions after the webinar, just feel free to send them to us in Eurosite or to reach out. You can see some links down there in chat that you can find some more information about living whales and the activities of the university. And I would like to share you the last screen. Just a moment. Okay, so the original idea is to have at least 2 more webinars every 2 weeks. Something happened. I'm not sure if you can see it. Just a moment. Oh, sorry. I will share it again. Okay, now you should see it. The first webinar is on habitat mapping using different remote sensing platforms by Jose Manuel Alvarez Martinez. And it is scheduled in 2 weeks at the same time, but we just received information that there might be slight change in time for this webinar. So sorry for that, but we will inform you just after webinar about the date, or we will confirm this one. And the next one on 31st March, also at 2 Central European time, on European units habitat suitability, probability modeling and mapping, and the European Vegetation Archive, EVA, by Sander Mucher and Stefan Hennekens. Maybe our colleagues would like to say something about this webinar? No, I cannot.
No, I don't think so. I think it's quite clear from the title. It's a continuation of activities in different projects. So we want to show the results.
Yes, thank you, Sander. So you are invited for the next 2 meetings. I hope also same intensive and great like today's meeting. So just after this webinar, you will get a reminder about the dates and titles and speakers for these webinars. And I would like to thank you all for this great time. Thank you, Richard, for your amazing work and speech. And Clive, would you like to add something as the chair of our group?
No, I don't think so, other than, like you say, to thank Richard for the presentation, which has stimulated a lot of discussion, and also to thank everybody for engaging and making it an interesting hour or two.
Okay, so thanks a lot, and we'll see again in 2 weeks, but the exact hour I will have to send you after the meeting because this sudden change. So we'll stay in contact, and great that you are with us, and see you again in 2 weeks and in 1 month later again. Thanks a lot, and see you all again, I hope. And please invite all of your colleagues and friends, because, well, I think that it's a great time that we are spending here together. Thanks a lot, and see you again. Bye.
All right, bye now.
Thank you, everybody. Thank you very much. Thank you for listening.
Bye-bye. See you.
Okay.
Thanks.
Yeah, cheers, Adam. Bye.
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 Thanks, Richard.